And so I'm pleased to give a very warm welcome to our speaker today, Professor Antony Hewish, who's of course a Nobel laureate. He was Professor of Radio Astronomy at the Cavendish Laboratory from 1971 to 1989. He was head of the Mullard Radio Astronomy Observatory here in Cambridge from 1982 to 1988. As he was just reminding me, his scientific career, of course, goes back much earlier than that as well. And he's been a Fellow of the Royal Society, indeed, since 1968. He's been the recipient of many prizes and awards, and I won't take up his time by listing them all here. But we're very pleased he's come to speak to us today, not simply on his scientific discoveries, but a more general topic, my life in science and religion, a personal story. So thank you very much, Antony.
Well, thank you all for turning out in weather like this to hear what I've got to say. And I should say immediately at the outset that I've no real brief to be talking to you about faith matters. I'm simply a hands-on physicist who's been rather lucky in his life, and I have no background in philosophy. But I was lucky enough to be brought up in a Christian family in Cornwall long ago, an Anglican church, and I've never found the slightest complications in being a physicist and also attempting to understand what religion is about and participating in Anglican religious services. My background goes back to the North Cornish coast and a small town in which I shared my upbringing actually with the famous choirmaster David Wilcox. In fact, David, the father of David Wilcox, ran Barclays Bank in Newquay, Cornwall, and my father took over the bank, and so I was brought up in the bank, and I don't know whether David Wilcox actually lived there, but I was brought up over a bank, living in a bank on the North Cornish coast, and I think I was amazingly lucky to have that background. When I looked out of my bedroom window, I could look out over the North Cornish sea and look at Trevose lighthouse about 10 miles away, twinkling on the horizon, and that's a memory which has lived with me all my life. But to come to the present, about 15 years ago, I had the good fortune to be invited as a guest to the opening of a scientific institute in South Korea, and another guest invited to the same place was Charles Townes, another Nobel laureate who is famous for inventing the maser. That's to say, an amplifier at high radio frequencies, which uses much of the same technology which is now we're all familiar with. Lasers, laser light is almost everywhere. It's in computers, and you all know, are very familiar with lasers. But Charles Townes as it were, set the ball rolling with his use of similar techniques in high radio frequencies. And I got to know him quite well because we traveled around South Korea together and gave lectures here and there. And we found wherever we went, to technical institutes and so on, the workers, the scientists, were desperate to know how you actually win a Nobel Prize. The first question almost that they asked wherever you went was, how do you win a Nobel Prize? And I always let Charlie Towns answer that question because he's much more senior than I am. He won the Nobel Prize in, I think, 1965, and he simply said, there's no magic about this. He said, do sensible research in a good team, and preferably in a subject which is fairly new, and sooner or later you may or may not win a Nobel Prize. But there's no magic about it. I mean, there are brilliant people who win Nobel Prizes. We all know them, like, for example, Einstein. But you don't. The point that Charlie Towns always made was that there's no need to be brilliant. Just do a good job, and with your physics, which is our experience, and if you're lucky and do your job well, Nobel Prizes will come. And I feel extremely fortunate that that's exactly what happened to me. There's no brilliance in my head. As I said, I'm not a philosopher. I don't move easily in the higher regions of mathematics, but I do enjoy physics, and I've enjoyed, I think, physics all my life, really. I had a very, very indulgent parents who set up our playroom ultimately to be a sort of carpenter's shop and come lab, and we were able to play around almost as how can I say this, with unlimited control. And I used to enjoy experiments with electricity. I'd been interested in electricity since I was about 7 years old. And because we lived on the first floor above the bank beneath, my work sometimes interfered with theirs. To obtain power for what I was interested in, I tended to dismantle the nearest electric light switch and connect wires to it and bring them to what I was doing on the bench. And anybody will know that this is fraught with hazards. And I sometimes fused not only the lights of our domestic lights above the bank, but also the bank beneath. And being plunged into darkness on a winter day in the bank is not good for trade, not good for business. But my father never said, you're forbidden to do these things. So I was very lucky as a child to be able to experiment and play around, and it was that, I think, that ultimately led to the Nobel Prize. I mean, I just enjoy investigating what I can with physics. But being brought up on the North Cornish coast brings you into contact with the sea and the wonderful world in which we live. And I think although we went to church every Sunday, my first sort of religious experience was actually on the golf course when I was a young teenager. My brother, I had two brothers, both older than I was, but I was nearest to the middle brother. I'm the youngest of three, and it was my middle brother who was keen on flying model aircraft in Cornwall. Being the youngest, of course, I had to toe the line and do more or less what I was told to do, and he wanted me to assist him in flying his model aircraft. We used to go to the golf course, and anybody who's lived on the North Cornish coast knows that it's rather difficult to get the right conditions to fly a light, elastic-powered aeroplane. There's normally half a gale blowing on the North Cornish coast, and we used to get up very early in the morning and go to the golf course where my father was a club member and I think treasurer of the local golf club. Well, at any rate, I mean, I didn't really realize this at the time, but when you're up before everybody else in Cornwall, and it happens to be a still, wonderful, beautiful morning, and you look out over the sea, you suddenly get a sort of feeling comes over you, and I didn't really know the adjective or adverb for this until I heard the word numinous explained to me by the late Charles Raven of this university. Charles Raven was a cleric who gave wonderful sermons, and he said we all get numinous experiences. You somehow feel the presence of a power behind the universe, a benevolent power behind the universe. And I can remember feeling much more, as it were, religious, flying aircraft on the golf course than I did in our church services at St. Michael's Church in Newquay. But at any rate, I was always conscious that there was something behind the universe. There has to be something, an intelligence. And religion brought me into contact with the sort of language in which this feeling began to make sense. Well, of course, one grows up, and I was sent away to school in Taunton, where we had chapel every day and twice on Sundays, so that I wasn't short of hearing the Bible being read, the 1662, of course, and I had a religious background, but I didn't really feel particularly religious myself. But how did I come to be where I am now? Well, when I left school, it was I got my reasonable school certificate, and this was the first piece of good luck. I wasn't clever enough to win scholarships to Cambridge, but at that time there was a desperate shortage of radio engineers to develop and operate radar systems, and you could get to Cambridge easily if you had reasonable educational background, and provided you read a subject called Physics with Radio. So I came up to Cambridge in 1942 to read for the Natural Sciences Tripos. And here another thing happened to me, which was quite by chance and worked in my favour, though I didn't realise it at the time. Because I'd been brought up on the North Cornish coast and I'd seen lots of regattas and things like that, I was dead keen on rowing. And I was really rather desperate when I came to Cambridge to get the feeling of rowing in an 8, because I'd seen the pilot gigs rowing races in regattas, and it's really wonderful to see pilot gigs on the open sea with crews not of 8 but of 6 actually, but to see them racing with a lovely rhythm, and this caught my imagination, and I was determined to row when I got to Cambridge, which I did. And nobody knows better than I that academic studies and rowing don't really go together. You have to spend too long on the river, which I did, and that meant that my examination result after 1 year was not really good enough to justify my continuing for the Tripos. People who you needed then to be rather clever to do the Natural Sciences Tripos and get an honours degree in 2 years. It's a 3 years course, but they had an accelerated collapsed course in 1942. So I was sent off to the wars, and the first place I went to was the Royal Aircraft Establishment to use my radio in a practical way, and I did rather dull things like seeing how high you could take the receiving equipment before it began to fail because of electrical discharges and such like. But after 6 months, and this was my best piece of luck, I was directed to TRE at Malvern, which was then, TRE stands for Telecommunications Research Establishment. That means nothing. It was the home of radar during the war, and in 1943, well, in fact it was 1944, I was directed to TRE, and my job there was to work with scientists to get to know a piece of equipment and then to introduce it to the Air Force. And what you can see behind you here, am I in the way, is the first thing I dealt with. This is...
Sorry.
I've got to stay here, have I?
No,
No, that's fine. No, that's fine.
You can move back over, it's okay.
You
Can
can
I?
go back.
Yeah.
Yeah.
This was the first thing I was involved with. It's a radar system at the tail end of a B-17 bomber. The idea was that you flew these jamming equipments to stop German night fighters homing in on our Lancasters when they made their night raids over Germany. And the idea was you simply transmit as much power as you can, but the signals are just nonsense. Noise is what we call them. Such signals now, totally random radio transmissions, which would just blank out any night fighter coming in, homing in, trying to home in on the bomber stream. Well, now this taught me a little bit about electronics, and this is the tail end of the same aircraft. it's called airborne grosser for reasons I don't understand. But in order to test the antenna system, you have to stand behind the aircraft while they run the equipment. That means revving up the port-inner engine, which is the one on the left-hand side nearest the fuselage, and you stand in the slipstream with dead rabbits and things being blown past you, and try and check that it's working okay. That's quite interesting, but then you have to go with the ultimately, when the equipment is manufactured and installed, to the bomber command stations where it's being operated. And I came to what was called a 100 Group Bomber Command, which is close to Norwich. And there's an airfield at a place called Alton. It was called, it's always been called Alton, but it was a 100 Group Bomber Command. And I flew a little bit there, testing it, and wangled some flights also. And but of course we wouldn't, as civilian scientists at GRE, we weren't allowed to fly on operations. So I had a good background, as it were, in practical electronics, and also perhaps a little background in teaching. But this is the sort of life I had. Now, when I got back to the university in 1946, the war over, I was a wiser man. I didn't waste time rowing on the river. That seemed a childish thing to do. I knew more electronics, and I got quite a good degree at the end of that, and I had the chance to do research. And the good luck was that because my tutors had said, I don't think you're really research standard, I wouldn't bother with thinking about that if I were you. So I was looking around Cambridge before my examination results came out, and I had almost accepted a job, but I got the chance to do research. And quite unknown to me, a new subject was beginning at that time. This was 1948 when I'd finished and got my good degree. I started research with Martin Ryle at the Cavendish. Now then, something which I didn't know about at all was that an interesting discovery had been made during the war. Radio waves from the sun jammed radio equipment occasionally, and this was first discovered in 1942. When the war was over, it was natural that this made a good sort of field of research for scientists who knew about the technology that was available then. And there's been a tradition at the Cavendish lab here in Cambridge to study the upper atmosphere, the Appleton layers, so-called. Edward Appleton was a research scientist at the Cavendish in pre-war days, and there was a group of ionospheric physicists not so far from here, making experiments by launching radio waves up into the atmosphere and getting reflections back and studying the ionized layers. But this group also turned its attention to radio waves from the sky, and that was when I first realized that someone... Hello?
It's okay, carry on. Just carry on. Carry on.
Well, can I make the next picture?
I'll bring it up.
You'll bring it up?
You just give me a moment.
Yes. Knowing nothing about these waves coming from the sky, I hadn't any ambition to be an astronomer or anything like that. This was another of these strokes of luck that just at the time I was looking for a research position in the Cavendish, I realized that a man I'd met during the war, whom I knew to be absolutely brilliant, Martin Ryle, was beginning this new subject of radio astronomy and making a systematic study of waves coming from the sky. At that time, the time I joined, almost nothing was known, and this was the beginning of a revolution which we're still really in which we're beginning to get real knowledge about the universe itself, and the fact that it began with instantaneously about 15 billion years ago, 14 billion years ago. My job as a research student was simply to join in with the team that Ryle had in those days, and I think I need to go back a bit there. Yes, there on the left is, as you see, the tall man is Martin Ryle. Unfortunately, no longer with us. He died in I think 1984. Next to him, with the soldering iron, is Graham Smith. They both became Astronomer Royal, but the research group which Martin Ryle was establishing was famous for starting modern observational cosmology on its course, which it is still on today, and deciding between such theories as Fred Hoyle's, is the universe being continuously regenerated, or did it have an instantaneous beginning? And the work that Ryle and Smith, or rather less so Smith, the work that Ryle did proved conclusively that we had to have a universe which had an origin in time. If you like to put a Christian view on that, it was created about 14 billion years ago. Now then, that was extremely good luck for me to be part of this team, but because I'd always been experimenting myself, I wanted to do my own thing as well as participate in the others. But we were, in fact, Martin Ryle had the skill to generate and you might say the humanity to generate a really good group around him. So here you had what Charlie Towns called the right background for Nobel Prizes. You had a good team doing sensible research in a new area. This shows you the sort of team activity that Martin Ryle would always generate. The whole group was required out on site. This is just behind the University Rugger Ground, not far from Grange Road. And whenever there was a major job to be done, and this was one of our earliest radio telescopes, there were 4 instruments like this. They were all built down East Road with the agricultural engineer Don Mackay, and it was designed on the floor of the workshop, really, essentially, at Mackay's. But whenever you were working on theory or whatever you were doing, you were required to turn up and work at whatever manual task Martin Ryle thought was important on that day, And in this case, it's altering the elevation of these structures so that you can make observations of different parts of the sky, and we couldn't afford to actually put motors on it and make them controllable. Martin Ryle's, the essence of his research was get results rapidly and without spending too much money, which we didn't have. And so he was doing this sort of thing while Bernard Lowell was dreaming about steerable dishes, and this was highly successful. But it generated a team of theoreticians and more practical people who all knew each other fairly intimately, and was extremely pleasant to live with. And we used to gather together on Saturday mornings and discuss the published work. We had paper reviews, publication reviews, and it was really a lovely place to be. But in my own particular work took me in a slightly different direction. But first of all, I should just mention, well, I've got some pictures to show. This, I was responsible. This picture was taken, must have been around about 1950 or thereabouts. I was responsible for the focal arrangements where the radiation is collected. What you can't see is the reflecting wires, which are supported by those hyperbolic structures. And as you can see, I'm pretty high up because I can actually look down on the whole thing. But I was responsible for those structures at the focus, and so I spent a lot of time climbing about on instruments like this, which had nothing to do with my own research. But while we're looking at this picture, you can actually just see, if you're sharp-eyed, a sort of shadow up on the left-hand corner there, which is the University Library Tower, just to the left of that tree there. But you see the two German antennas on there and there at the very top of the picture. They were used by Graham Smith, whom you saw in the first slide, and they were they first showed that the radio sources we were looking at were on the verge of detection with the most powerful optical telescope in the world, which was the famous 200-inch telescope on the west coast of the United States. In other words, with extremely simple equipment, you could get to the edge of the universe and begin to observe features of first-rate importance for cosmology. And in the next few years, the steady-state theory was shown to be invalid. As you look to greater and greater distance in the universe, you could see that the distribution of radio galaxies was not consistent with a universe constantly regenerating itself. I won't go into details, but it's a very simple and straightforward observation once you have a telescope of sufficient sensitivity. And this was Martin Ryle's skill to develop such instruments. Well, now, I'm talking about my own practical work and contribution to this, but my own research, because I wanted to do something quite different, was to use these newly discovered radio sources to investigate the ionosphere, which were the ionized layers about 300 kilometers above the Earth's surface. And I realized that there were ways of doing things which just hadn't been done before, and I just wanted to see. It was rather like my experiments which plunged the bank into darkness. I just wanted to see how useful these radio waves could be in investigating the ionosphere, having come from outer space right through the whole of the Earth's atmosphere, was a new way of looking at it. And it turned out that the twinkling of these radio galaxies, due to clouds in the ionosphere, was something which hadn't been seriously studied, and I got to grips with that, and that was my doctoral thesis. And I can clearly remember cycling back down the road past the rugger ground late one night, the first time I had measured the speed of these clouds over the ground, and realizing that because I was sampling the atmosphere at greater heights than had been possible before, and I'm now talking about 1949, 1950. The wind speed was something like 300 kilometers per hour, which is quite fast, and I was the only person in the world to know it that night, because nobody else could sample that atmosphere. It was much too high for direct sampling by aircraft, and spacecraft, of course, hadn't been invented then, and with relatively simple equipment, just close to where we're sitting, I was able to do these things. And my own work continued with that, and what's happened now?
I think it's run out of power.
Yeah.
So she's getting a power lead.
Power.
Yeah.
Yes.
No, she's getting a new power lead.
Okay. Well, I don't know if what I'm saying is making much sense, but I see that time is running out. All of this work, ultimately, as far as I was concerned, I extended these methods that I'd used for the Earth's atmosphere to the Sun's atmosphere, and in so doing discovered that I could measure the angular size of radio galaxies with much higher accuracy than was possible with any equipment on the ground. I won't go into details. It's simply a question of the way radiation propagates through the Sun's atmosphere and causes a twinkling effect, which you can use to measure the actual angular size of radio galaxies as seen in the sky. And in the 1960s, there was enormous interest in objects called quasars, which happened to have tiny angular sizes. They didn't look like galaxies, they looked like stars, but they really were galaxies. And this was an enormously powerful way of detecting which of our radio galaxies was actually a quasar. And without spending very much money and without enormously sophisticated engineering, I simply designed an antenna to cover a whole field. It was called the 4.5 acre antenna. And the idea was to measure this scintillation, twinkling effect on the largest number of galaxies I could see, which would be about, in those days, about 900. And from those measurements, I could tell which are the interesting galaxies, which are quasars, and which are not, and so that attention could be focused on the really interesting radio galaxies. We now know that those are the galaxies with active black holes at the center of them. But this antenna of mine was also extremely useful because it led to the discovery of pulsars. Tiny stars which rotate rapidly like lighthouses, really, producing a beam of radiation which you detect because they radiate just short, sharp pulses as the star spins. And it turned out that I discovered a new sort of star by looking into the sky. This was something totally unexpected, and just one of those bits of good luck that Charlie Towns mentioned. And it was that discovery which, of course, led to my Nobel Prize, but it was a gift from heaven, as it were. No one had anticipated that any object in the sky would behave like this before, and it opened a new chapter in astronomy. But to come back to religion and the relevance to all this, the main point of what I want to say is that while Polkinghorne and others regard science and faith as complementary, I would go a little bit further and say that science is actually a help. It's a great help to understanding religion, because as we all know, there's a huge amount of mystery in religion. That concepts of God are mysterious. The fact, the essence of the Christian faith, that God revealed his purposes through the life of a man, a real man who lived 2,000 years ago, or thereabouts. This is something we have to accept, and there's real mystery here. But even the most basic physics is mysterious, and because we believe, we know that the physics is right, then we should not be afraid of mystery. Which and that seems to me where atheists like, for example, Dawkins, fall down, because they regard this sort of mystery as fairy tales, which we should not believe. In fact, physics itself, at the most basic level, is almost unbelievable when you look closely at it. And for example, take a glass of water like that. You wouldn't think there was much mystery, would you, in there? But there's a lot of hydrogen atoms in there. The hydrogen atom is the simplest atom that you can imagine. It contains a proton, loosely speaking, with an electron in orbit about it. That's a very crude description, but it's good enough for now. But modern physics, quantum physics, tells you there's more going on than that. When you push quantum limits, when you push quantum physics to the limit, it is saying things like there's no such thing as a vacuum. If you empty a room or a box of all material objects in it, if you could, there would still be quantum waves, just because theory predicts it. And these quantum waves cover the whole spectrum. And in actual fact, an electron in orbit about a proton is sensing these quantum waves, which are causing, how does one say this, are causing virtual particles to come into existence and then fade out of existence virtually instantaneously, but long enough in existence to be effective in moderating what goes on inside an atom like hydrogen, inside that water. That water is subject to an immense sea of virtual particles which fills space, and even in a total vacuum. And that discovery resulted in another Nobel Prize. This effect is called the Land shift. You can actually measure the properties. As the electron orbits the nucleus, the proton, it is subject to these virtual particles, this sea of virtual particles, which come in and out of existence much too rapidly for any detection. But as they exist, they generate an electric field which affects the energy of the orbiting electron about the proton, because it's an electromagnetic effect, and therefore matter, even at its most basic, simple level, is much more subtle and involves a mystery that is predicted and observed to actually happen, but you would never have dreamt that this sort of thing would exist. You have to pinch yourself to realize that it exists. And physics is full of things like this. Experts in quantum theory have said that if you really understand what quantum theory is saying, then you simply cannot believe it. And this, I think, is an answer to the atheistic view that religion demands too much in the way of mystery to be believable. So physics and faith are not just complementary, but they are also, physics helps you to get into the right frame of mind to realize that religious mysteries can exist and be reasonable without defeating common sense. Common sense would say these ideas are rubbish, but the measurement tells you this is actually happening. And I could mention further, I'm not an expert in theoretical physics. There are many examples of this sort of activity, and we often hear about quantum entanglement. I don't know if you've heard about that, but a particle which you have in the lab can affect a particle on the other side of the universe instantaneously. If you generate two particles like an electron and a positron in the same interaction and they fly apart, what you do to one is noticed by the other immediately, instantly. Its direction of spin, for example. And if you make measurements on one particle that you have in the lab, its mate on the other side of the universe will know about it immediately. And that's a total mystery. But we know that to be true, and experiments have demonstrated it. So physics is an ally to faith, not an enemy, and it isn't just complementary. And to believe that our rational common sense is all that there is just rubbish in my view. Philosophers like Bertrand Russell have says what we can't learn by science isn't worth knowing. That just isn't true. Science cannot explain certain things, and that really is the core of what I would like to say. You have to be able to observe, to believe mystery, not only in physics, but because you can actually verify it, but also that makes one totally acceptable to mystery in faith. And I think that's a very useful thing to know. I see I'm over time already, so I must stop there, but I hope what I've said may mean something to you. But going back, I've had a wonderful life in science, and I've tried to help in religion. I've been...
Sorry, my fault.
I think you need some better electronics. What was I saying? Where was I?
I tried to help in science.
Sorry?
You said I tried to help in science.
Oh yes.
Yes.
Oh, I've tried to help in faith. I've been anybody who's attached to a church knows that if you turn up more than two or three times, you're asked to do things. And so I've been church warden at St Michael's Church, close to the Arts Theatre, for more than 10 years. Before I left living in Cambridge and went out to live in the country at a tiny village called Kingston. I was church warden there for 25 years, so I've done my best, as it were. Religion is certainly alive and well in certain churches and villages that I've had experience of, and physics, to my mind, at least for me personally, has been a great help in preparing me to accept mysteries which none of us fully understands with regard to faith and religion. Thank you very much.
Should use that. So we have a little bit more experimental work to do, I think. So, okay, we have some time for questions. Brief time, so over to you for anything that's been. Please, yes, question here. Yes, please. Yes, that's you. Yes, yes.
You were saying about how physics is full of mysteries, and obviously as human beings, like there must be a limit to how much we can understand. We're only a sort of biological organisms. It's difficult to understand a rhino understanding quantum physics. So, do you think there's going to come a point soon where we're going to kind of reach, in terms of physics, a level that we just won't be able to understand past?
Okay, can I summarise the question?
Yes.
Yes, so I think the question is, so we can understand a huge amount about physics, a huge amount about biology. Are we going to get a limit to our understanding where we simply say that's as far as science can go at all? The end of science sort of thing. Is that the gist of the question?
Science, but sort of the end of how much we as human beings can comprehend.
What are the boundaries of how much we can, as human beings, can really understand? I think that's the gist of the question in areas of physics and biology.
I would like to say no. I mean, if you think of our view of physics now and compare it with Newtonian ideas, they're simply poles apart. And who knows what the next few centuries will bring. I think it's rash to say anything like that.
So we'll all have jobs for a long time then.
Okay, another question. Thank you. Please, over here. Thanks, sir. Yeah.
I believe in God myself, but I'm intrigued about this idea of mystery in both religion and physics and science, but kind of taking the sort of atheist perspective just for a second. Why would you accept the mystery of religion? I mean, the atheist might argue and say that the mystery of science is, we are led to it by evidence, whereas the mystery of religion, the atheist may argue and say that the evidence towards it isn't good. So what response would you have to that?
Yeah. So the question is basically saying, well, taking the position of an atheist, the atheist could say, well, the evidence we have in science points towards a mystery, whereas religion doesn't have any evidence, so it's in a different kind of category. So can you really make a comparison between mystery and science and religion? Is it a valid comparison? Science is all about evidence, religion is about something else.
Well, that's a good and hard question to answer. But my feeling is that the atheists, such as the famous Oxford Dawkins, don't really make that decision and make that distinction, and think they talk about superstitious nonsense in religion that we should drop. I think in the light of modern physics, the word nonsense needs extremely careful handling, because modern physics seems to be nonsense. I mean, I sometimes think that the string theorists, which is the way we look at theoretical cosmology nowadays and particle physics, looks like nonsense to me, and I hardly, when people talk about a multiverse, are we talking physics or are we talking nonsense? I really don't know, and it's a tough question.
Okay, please, yes, one more question. Yeah.
Thank you very much. Does it help to make a distinction between the rational, the irrational, and the non-rational? Because I don't think, as a person of faith, I would ever espouse the irrational when I define the irrational as either prejudice or clear contradiction. And on the other hand, there are many things that are non-rational, like particular experiences, which are not in themselves either something that is consistent or inconsistent, but is a raw material for reflection. And when people talk about mystery, I think sometimes they're too quick to say it's a rational or an irrational matter, when it's really something, a third, a tertium quid, a third thing of the non-rational. And we are never, or should be, never encouraged to believe irrational, prejudice, plain contradiction, but open to the possibility that there are new ways of seeing things which will introduce an element of rationality into the non-rational.
I think I totally agree with that. But you're talking like a philosopher, and I soon get lost when philosophers talk to me.
Well, yes, it's a useful distinction. We'd love to. A lot of hands going up, but honestly, we do promise people we finish at 2, simply because we know a lot of people have things to do. If you have other questions, can you stay around for a few minutes just to chat? Yes. So do come up and ask the speaker afterwards, and I'm sure he'd be delighted to help. But let's really thank Antony Hewish for a fascinating talk.